Okay, should we talk about this one?
Yeah.
Okay, so real quick, remind me, what are we, when we're trying to find the values of x guaranteed by the mean value theorem, what's the mean value theorem again? What's it say? If a function is,
Smooth and continuous.
okay, so smooth, meaning,
Continuous and.
smooth. Okay, good, so let's be very specific. So, the mean value theorem, the criteria we have to meet for smoothness on an interval are that the function has to be continuous on the closed interval and differentiable on the open interval in between, right?
Yep.
Okay? So, is this function, just looking at f of x, are there any potential problems with f of x here? You're right, no.
No.
How do you, and justify that, how come?
There's not an X on the bottom or even root root.
Yeah, okay, so we don't have any, no red flags, right? We don't have any x's or functions of x on the bottom, right?
Right.
Meaning, in terms of trig functions, we don't have any of the asymptotic trig functions. We've got, of the 6 trig functions, we've got the 2 base trig functions, right? The sine and cosine, and then all the other ones are built from some quotients of those in some form or another, right?
Yep.
Sine, or tangent, cotangent, secant, cosecant, all involve, in some way, shape, or form, they all involve either a sine or a cosine on the bottom of a fraction, right?
Right.
Okay, so those are the ones that have asymptotes. Sine and cosine don't. Sine and cosine are well behaved. So f of x gets the all clear, right? No problem there. So we've met the first part of smoothness. The function is continuous on this closed interval. Now we have to see if it is differentiable. So what does differentiable mean?
Take the derivative.
Take the derivative of one. Good. Okay, so can we take the derivative?
Yes.
So, and really, remember our trick here on this one. The trick is we're going to differentiate, and then we're just going to ask ourselves, okay, well, is the derivative continuous, right? A continuous derivative means a differentiable function, right? So let's differentiate. What is f prime of x? First term. Okay? Okay, minus sine
Sine 2x.
2x times 2. Right, because I have to multiply, I have to, by the chain rule, the derivative of 2x is 2. Okay, so there's my derivative. Now the derivative, what are we trying to, okay, that's continuous everywhere, right? So we check. We met the criteria for the mean value theorem. So now the mean value theorem guarantees us something. What does it tell us? It's an existence theorem. All it does is tell us that there's something that exists, but we still have to go find it. Make sure it does. Okay, I guess in a way, I mean, it kind of is saying that, but technically it says that on this interval, there's going to be at least one value of x where what happens? Well, okay, I mean, it may or may not be extrema. Extreme is really not the right answer. I shouldn't have said that. That's really not what we're looking for.
It's like a value of
No? The mean value, what does mean mean? Average. Okay. Good. So there's going to be one place at least where the average rate of change of the function is equal to, no. Let's go back and, I think I need to redraw the picture. Yeah, I'm a big fan of pictures. I'm going to draw this picture. You guys fill in the blanks here. I think that the pictures that go with these existence theorems are usually, that's the way to remember it. You can draw the picture, you can get the theorem. So here's our function. And let's say we're going to go from A to B, right?
Okay.
So I've got a point here and a point here. And all that the mean value theorem is saying is that the slope of the secant line, which is the average rate of change, right? And let's write that. So average rate of change, which is the slope of the secant line. And so I guess I need some points there. This is A, so what are the coordinates of that point? And this one would be,
B, F of B.
so then the slope of that line would be what? Good, okay, so, good, so if we made a slope triangle, we've got the rise, which is just f of b minus f of a over the run, which is just b minus a, right? Must be equal to what? This is the average rate of change. There must be at least one place, call it C, maybe multiple. Okay, the tangent line. Good, is equal to the slope of a tangent line. Now, what do we call that? The slope of the secant line is the average rate of change. It's just total change in the function divided by total change in x, right? Like average speed would be total distance divided by total time. It has nothing to do with how fast you're going at any one particular instant. It's just how fast on average you're going over the whole trip, right? So what is this guy up here then? Because you can see on the picture, that's about where it is, right? So those are going to be parallel. So the slope of the secant line is equal to the slope of the tangent line. What does that represent at this point of tangency? What kind of a rate of change?
Equal.
Now, this is an average rate of change.
Parallel.
What's that? Instantaneous rate of change. Okay, so that's the rate of change at that one particular instant on, so it's like a speedometer, right? The speedometer is continuously changing along your journey, but as you look at your speedometer, it's telling you the instantaneous rate of change for every moment of the trip, right? Okay, so that's what this is telling us. So this is the instantaneous rate of change, and that's represented by what? Let's call that point right there C. How do I represent that slope? Yeah, so it's just going to be f prime of C, right? We got to find all those values of x, call them C, where that's true, where the green equals the red, right? Okay, so then what's that become? So our equation, for us, we didn't graph it, but that's our function, right? So the instantaneous rate of change is just going to be f prime of x. We got to find it, right? We're finding all the values of x where this works. So f prime of x needs to equal f of b, well, that's f of pi, minus f of a, f of 0, divided by pi minus 0, right? Okay, so we can be specific. F prime of x, we know what that is. F prime of x is just that, right? So it's 2 cosine x minus 2 sine of 2x. And that's equal to, going up to our function, what is f of pi? What's sine of pi? 0. What's cosine of 2 pi? 1. So I'm going to get 1 minus, what's sine of 0?
0.
0. What's cosine of 2 times 0? 1. 1, right? Cosine of 0 is 1 divided by pi. So I get an answer of
0 divided by pi.
0 divided by pi is 0. Good. So that's the equation that we're solving then, right? To find and we know we're going to get a solution. We have to get at least one solution because the math gods guarantee it through the mean value theorem. So we're going to solve this equation. 2 cosine x minus 2 sine 2x equals 0. Okay, so this it's been a while since you've probably done stuff like this, solved trig equations, right?
Yeah,
Definitely a while. So how do we go about, question, Clancy?
Yeah, real quick, where did you get the 2 cosine x versus 2 sine 2x right before the?
That was just when we differentiated,
Oh, so you
right? We just differentiated the function to get the.
okay, and then you plugged in pi at 0.
Yep.
Okay.
Yep, then we plugged in, and then we calculated, this is gonna be a number, right? We calculated the average rate of change, just the slope of the secant line.
So you took pi into the blue one, and then you got 1, then you put 0.
Yep.
And you got 0. Okay.
No, put them into here.
Oh, you put it into the black one?
Yeah, we put them into, see, that's, because that's the function, this is f prime, this is the derivative, right?
Oh,
Remember, the slope of the secant line has nothing to do with the derivative, right? That's a non-calculus issue. That's just the rate of change of the function. How much is the function changing over a numerator?
Trinity Tree Lore, Deshaun,
Y, you
Dick,
can change
and
the
Cameron,
function.
please come to the office.
Okay, so if we go back to our picture real quick, maybe that picture's good. If we go back to our picture, the slope of the red line doesn't involve any calculus,
Right,
right? That's a secant line. It's the slope of the green line that requires us to do calculus,
right.
okay? The tangent line, okay? Okay, so now let's talk about this equation, because why is this a really awkward equation to solve? Okay, there's one thing that's going on. What's that?
The 2x.
Okay, that's huge. That's a big red flag. Because we're not even using the same kinds of angles here. We're taking cosines of apples and cosines of oranges. They're not the same, right? How are you going to relate cosines of x and sines of 2x, right? Okay, we really can't do that conveniently. What we have to do here, we have to be able to use trig identities to transform one of those trig expressions in such a way that the angle matches the other, right? You can't be trying to solve an equation that's involving, other than doing it on like a calculator or something. I mean, you can't have something like that and solve it. There's another small issue here that pops up, and that is that the cosine and the sine don't match up. That's child's play compared to this one. We got to deal with that. So what are we going to do? Yeah, good. Yeah, we're going to use a trig identity. We're going to use the fact that sine 2x equals what?
It's 2 sine x cosine x.
2 sine x cosine x. Yeah, that's that one. So we're going to rewrite this as 2.
Just alright.
Yeah.
Can't you move the 2 sine 2x over to the other side first and then cancel out the 2's?
Yeah, we could cancel the 2's right now.
Oh,
Yep.
yeah.
We can
I
do
guess
that.
you don't have to move it up.
Yeah, we can do that.
And then do it.
That's not a bad idea. Okay, so then we end up with cosine x minus 2 sine x cosine x, because that's what this gives us,
Oh, I feel you.
right?
But real quick, I thought 15 was not prime.
Say it again.
Why did we cancel the 2's not 2 without prime?
I just divided both sides by 2.
If you were going to get 2 sine x over,
Right.
or I guess you,
Okay,
since
so
it's
2
0.
divided by 0.
Because 2 is a common factor to the left side.
Okay.
Okay, so now what? And then what are some options here? What can we do?
You can just move it goes down further
To the other side? Okay, let's do this. Suggestion is cosine x equals 2 sine x cosine x.
You can divide by, yeah.
Okay, so divide by cosine x,
And you just have 2 sine x.
and then I just have 2 sine
You
x.
still have a cosine x.
Oh, no, you have.
It'd be 1 equals sine.
It'd be 2 sine x.
Okay,
You get 1.
does
One on one side, so.
does anybody? So here's the suggestion. We're gonna.
No,
The suggestion is we're gonna cancel divide both sides by cosine x, so we get 1 equals 2 sine x, right?
no, that's wrong,
Okay, but what's the problem with that?
because you have a 2 cosine now.
You still got a
Well, I've got a sine, and then you could divide both sides by 2 and use a trig circle, or get a circle.
What?
It's a 2 cosine x. The 2 is applying to the cosine x, 2 isn't it?
No, hang on.
Oh.
No.
Are we getting too complicated or?
Listen. So on the right side, how many factors are there?
3.
3.
2.
Including the 2, there are 3. I've got 2 times sine x times cosine x.
Oh, wait,
So I can divide both sides by cosine x. If I multiply three things, real quick, what's 2 times 3 times 4? 24. It's not 48. So I don't double multiply the 2, right? That wouldn't be correct. That makes sense, Riley?
Yeah.
Okay, so. Okay, but we could wrap this up. We could divide each side by 2 and get 1/2 equals sine x, and then just go to the unit circle, right? And on our interval, from 0 to pi, where does sine equal 1/2? So we're going from here up to there. No. So pi over 6 would work, or 5 pi over 6. Okay, but we missed something. We missed something here. Those are two answers. We did something. I started writing this in red because it was wrong. Okay, no, I want you to be aware of this. This is really important. So it's not okay to divide both sides of an equation by cosine x. How come?
Because sine x, cosine x are 1.
Well, okay, I mean kind of, but because I divided by a function of x, right? So I lost some solutions. When you're doing algebra, you can divide both sides of an equation by a constant freely. That's fine to do. But you cannot divide both sides of an equation by a variable or a function of a variable, because then you're losing solutions to the equation, right? I'll give you an example. What if we had something, just pick a non-trig example. I gotta think one here. What if we had x cubed minus, I'll just do x squared. X squared minus x equals 0. What you guys just told me to do is you said, add the x to the other side. So I'd get x squared equals x, divide both sides by x, and get x equals 1.
Yeah.
That's only partially right though. Because how should I solve that?
Plus or negative 1.
No. What should I have done up here?
No, you should have taken the factors out.
I should factor it. I should have factored out an x, which would have given me x times x minus 1 equals 0. So either x equals 0 or x equals 1. There are two solutions. I lost a solution by dividing both sides by x. Can't do that,
Let's go fix it.
right? So let's go back, let's fix it.
Can we build
Okay, so what should I do here then?
Together cosine.
Yeah, I'm gonna factor them. Factor out a cosine x. So if I factor out a cosine x, I'm left with 1 minus 2 sine x, right? And now we're okay. Now I can solve, I've got a factored equation, so I'll just apply the zero product property, right? I'm just gonna answer the question now, when is cosine x equal to 0? Or when is 1 minus 2 sine x equal to 0? We already did that one, didn't we? That's the one we just did. This was when sine x equaled 1/2, and our answers were on our domain, right? Our domain only goes from values of x greater than or equal to 0 and less than or equal to pi, right? So on our domain, you already told me that that one looked like that spot and that spot, right? So x equals pi over 6 or pi minus pi over 6, so 5/6 pi. Okay, what about this one right here? Where does cosine of x equal 0? Cosine equals 0 at right there, doesn't it? Right? At pi halves. So from this one, I get the solution x equals pi halves, right? And so when I make my table then, if I go clear back up here, when I make my table, So when I make my table, actually, we're doing, oh, never mind.
Never mind.
No table.
We don't need a table. We're not doing, what am I saying? We're just doing mean value theorem. We don't have to go any further.
Yeah.
Our answers were,
Pi over 2, pi over 6, pi over 6.
yeah, pi over 6, pi over 2, 5 pi over 6. Those are all the places on the interior of our domain, right? Where the value of the derivative equaled the value of the average rate of change, right? Slope of the tangent line equal the slope of the secant line, okay? The thing I really want, I mean, it's probably good that we went through the problem, but the thing I really wanted to show you, two things, is how do you deal with a trig equation like this guy? And remember, we had to do, the trick was, the way we had to do this is we had to trade the sine 2x for sines and cosines, so that we got a trig equation that we could factor and solve by the zero product property. Okay? Okay. Make sense? Question, Hunter?
Can you show me how it's 5 pi over 6? I'm actually good.
Yeah, because, okay, so if we look at the unit circle down here, we just want to know when is the sine, which is the vertical component on the unit circle, equal to 1/2. Well, that's going to be at this angle right here, which has coordinates 1/2. You know what? We messed that up, didn't we?
Yeah, I feel like it's pi over 3.
But still, I feel like.
I don't even.
Oh, no, sorry. No, that's right.
You know?
That's right.
No, it's right. I
It's
didn't want
right.
a calculator. I'm just.
It's right. So this should have been square root of 3 over 2, 1/2, right?
Yeah.
And this one would have been minus square root of 3 over 2, 1/2. Just from unit circle stuff, right?
Wait,
Yeah.
is there another way to do it? Like how?
Do the triangle.
You do the triangles, but that's not. It doesn't help when you need 5 pi over 6.
Yeah, I wouldn't do the triangles. I would do the unit circle. I really think that if you don't know the unit circle well, I mean, just learn it. I would just print out the one that's online if you need to, but just know those spots on the unit circle. And I think I showed you guys that if you know quadrant 1, you know all 4 quadrants.
Is there a song for it? Like the.
There's not a song for it, unfortunately. Can we make up a song?
Yeah, I feel like that would really help.
Yeah.
Should we just ask
And the remaining 14 minutes of time.
Coming up with a song?
Yeah.
Okay, I got something else for you.
Will you
Well,
explain
we're-
something
Yeah,
about
you
this?
can start it if you
Yeah.
Can you just come here? Because I'm not answering to explain.
Try it.
Help me to-
It's pretty fun.
Okay, is it something you can, was it on this page?
Yeah, it's up near the top.
Okay.
It's right up there. It's the f of pi and the f of 0.
Oh, right here.
Because when you put pi in for cosine, you get -1 though. You don't get 1, you get -1.
Did we mess up the whole
Oh,
thing?
God.
Am I confused?
We don't have to go back to this one.
Did we get this messed up? F of pi, so if we put pi in here
You don't
Oh,
plug
it's
it, you just
sine.
plug it into the blue.
Yeah.
You just plug it into the blue. You don't plug it into the blue. You plug it into the black.
to the black, yeah.
Okay.
There's several of them.
Okay, but don't you have to multiply by 2?
No, that's 1.
Oh, front.
I just put it in my calculator. It's 1.
No, because you see how the 2's out front though? So why didn't you multiply it by 2?
You would.
So then why is it 1 down there?
Oh,
Because sine pi is 0.
sine pi is 0.
If you do 2
Yeah.
Sine pi is
So,
0.
okay, sine pi is 0.
But
0
then-
times 2 is 0.
Cosine of 2 pi is 1. See what I'm saying?
Yeah.
So when you plug this in, if I plug pi in, I'm gonna get 2 sine of pi, which is 0, plus cosine of 2 pi, which is 1, minus this function evaluated at 0, which is 2 sine 0, 0, plus cosine of 0, 1. So I'm getting 1 each time, and right?
Okay.
Does that make sense?
I see what
Okay.
it made more sense.
Okay, so here's what I want to look at next. Let's take a look at this. Yes.
Not to distract you, but we found an awesome unit circle song we'd like to share.
A song.
Did you really?
Yeah, there's so many.
Zip Jones found it.
Is it good?
It's pretty good. It's like pretty catchy.
Okay, so do I go to it on here? Can you find it on here? Okay.